Uh, Welcome to SUPRA SAE India 2015 webinar training session day 4. I am Apur Bapat. I am working with Altair Engineering. So let's start today's session where I am going to show you how you can perform the analysis on knuckle and hub, or you can say upright as well as on the hub. So in this session, you are going to see how to do 3D meshing on the models, then the types of 3D elements, when to use 3D elements, how to perform the analysis with 2 or more loading conditions, how to create rigid elements. So these are the things which we are going to see in today's session. So let's start with when to use 3D elements. So 3D elements should be used when all the dimensions are comparable. That is, X, Y, Z are comparable dimensions, then we can use 3D elements. So the element shapes are available on for the 3D elements are tetra, penta, hexa and pyramid. Additional data which is required from the user to provide as an input in 3D element is nothing. You don't have to provide any other inputs for 3D elements. Element type is solid, and some practical application is gearbox, engine block, crankshaft, etc. You can see here. Now we'll see the different types of 3D elements. So there are basically 3 types of 3D element. Pyramid is still in process. It's not available still in CAE softwares. So first is tetra element. There are 2 segments in tetra element. One is linear tetra, which is having 4 nodes. Then a parabolic tetra, which is having 10 nodes. Then penta element, which is having 6 nodes, that is linear penta. And a parabolic penta is having 15 nodes. Then we have a hexa or brick element. Here also linear hexa, 8 noded element, or parabolic hexa, 20 noded element. There is one very interesting point in solid elements, that is degree of freedom for solid elements. So the 2D thin shell and 1D beam element support 6 degrees of freedom, but a solid element have only 3 translational degrees of freedom, that is no rotational degrees of freedom. That is, a 10 noded tetra element has only 10 into 3, that is 30 degrees of freedom. So the question arises is, why does a solid element only supports 3 translational and no rotational degrees of freedom? So consider a piece of paper or a long steel scale. It could be easily bent and twist, that is rotational degrees of freedom. But now consider a solid object like a duster or a paperweight. It could not be subjected to very high bending or torsional stiffness. Hence, solid elements have been formulated with 3 translational degrees of freedom and no rotational degrees of freedom. So this is the reason why a 3D element only has the translational degrees of freedom and no rotational degrees of freedom. Now we will move to the next portion of today's session, that is how we can do the meshing and solve the model in of 3D element using HyperWorks Student Edition. So there are 2 ways of importing a model in HyperMesh. One way is you can go it from here, import geometry. Click on this icon. Browse, select the file type as IGES. Browse the folder, that is select file. Select the file wheel hub and click on import. So this is the wheel hub model. So the first step is to perform a geometry editing, that this surface or this solid has to be completely covered or completely packed throughout the entire geometry. So while you import a model from any CAD software in HyperMesh, it creates two geometries. First, a surface geometry and a solid geometry. So first, I personally suggest you to initially, as you are a new users for the HyperWorks tool, so always work on surface geometry because it is easy to edit the geometry as compared to solid geometry. So what I will do is, first I will press F2 from my keyboard, that is I will enter to delete panel. You can enter to delete panel from this cross symbol also. Then from the drop box I will select the solid objects, like solid option here. Click on solids and select all. So currently it is not showing that the solid has been selected, but if you have the solid, it will show the number of solids selected, and click on delete. So it will delete the solid, keeping only the surfaces. That is what we need. We only want to keep the surfaces, we don't want any solids. So now I have a geometry which is bound of surface. This is hollow. If I go to mask, surfaces, select this surface and say mask, you can see this geometry is hollow. This is not a solid. This is a hollow geometry, as you can see here. So now I will change the color, and first check the connectivity of my geometry itself. The geometry has to be connected properly. So to check the connectivity, I will go to the visualization panel. On the visualization panel, you will see 4 different edge colors and they are ticked. I will first explain you the different colors and what are the significance of that. So red color edge means free edges, that is the surface is having one edge shared to it. So that edge is sharing only one surface. Shared edge, that is a green color edge, that is here, means you can see. So this is a separate, both the surfaces are not connected. That red color edge is showing that these surfaces are not connected. Green color edge means this particular edge is sharing two surfaces. Suppressed, the blue dotted line edge represents that particular edge is suppressed, and you can select one single surface and you can retrieve that particular edge later on as per your requirement. Non-manifold, that is yellow color edge, represents that from that particular edge 3 or more surfaces are passing. So either it has to be a T connection, or if it's a duplicate surface, then also it will show a yellow color edge. So we have to check that my geometry should not have a free edge and non-manifold. If it's having a non-manifold, it should be in the correct location. So you can see it is having a free edge here. So my first point is to correct it. So to correct this, I will go to geometry page. On geometry page, I will click on quick edit panel. On this, I will select the option as toggle edge. And enter the tolerance value as 0.1. The tolerance value means the gap between the two edges. So I am allowing, if the gap is less than or equal to 0.1 mm, it will join it. If it's more than that, it will not join that edges. So I will just left click on this edge. It is asking that the gap is 0.2. So do you still want to toggle? I will say yes. So this will join the two separate edges and make it green. So this will, in this way we can connect the geometry throughout. So in this way, my geometry is completely connected. Now, to perform the 3D meshing, there are two ways to perform it. One way is via manual meshing, that is, first create the 2D elements and then you can transfer those 2D elements into 3D elements and then do the further analysis, or you can directly perform the 3D hexa mesh. So what I am going to do is, on this particular model, I am going to perform a 2D to 3D meshing, and on Knuckle, or sometimes people call as it upright, I am going to perform direct 3D meshing. So the first step to perform 2D to 3D meshing is, I request all of you to start noting the points. This is a step-by-step process. If you miss any step, you will end up with an error. So I am requesting everyone to start noting the points. If you skip any point, let me know. I'll repeat that point again, because this is very important process. So once my geometry editing is done, now I will go to 2D page. On 2D page, I will select Auto Mesh panel. I will click on Surface, All, enter the mesh style as R trias, element size as 10, keeping all the other parameters as it is. I will click on Mesh. So you can see the mesh size is very big. So what I will do is, here I will change the element size. From this portion you can change the element size. So I will enter the element size to 5 and click on Recal All, that is recalculate all, and say Mesh. So this is also fairly good, but I can still reduce it. So I will reduce it further to 3 and say recalculate all and say Mesh. So this looks nice. You can see here the meshing looks nice now. So at the edges, I will change the number of nodes. Making it even number of. So around the holes, what I suggest is always do even number of meshing. So even number will capture the curvature more instead of odd numbers. So you can set it directly from here, that is 6, and click on the edge. Enter 3 mesh. And you can see there are different lines available. So what I will do, once the meshing is done, I will again go to quick edit panel on geometry page and unsplit some of the lines. So editing the geometry, if I edit the geometry, I will toggle these lines will help me to do a better meshing. So geometry editing is very important part, and that helps you to create a better mesh surface. So those lines which you don't want, you can toggle it down. Also, I will show you some of the other geometry editing points, like first of all, I would like to mention that these components will not fail on the fillets. Like this component will not fail in these fillets, the small fillets. This component may fail either on this side where we are going to mount a disc, or the bold locations, and on this location these types of component is going to fail. So there is no point in meshing these areas. So what I will do is I will remove these areas and make it a flat. So making those flat will help me to do a better mesh. So what I will to do it geometry editing, I will go to geometry page. On geometry page, I will click on D feature. And select the second option as surface fillets. Click on find. Select the fillet and click on remove. This will make this flat. You can see here. Similarly, you can select these. So by making them smooth, or you can say by making them flat, so as these are not getting removed, so what I will do now is I will toggle these lines. So press F11 and toggle these lines. So these small distances I don't want. So this will help me to do a better meshing with auto mesh panel. So again I will press F10 from my keyboard, shift left mouse button and drag to select all the surfaces and click on mesh. So you can see it has created a better mesh as compared to the earlier one. Also I can change the element size now. So I'll accept this meshing. So this is quite a good mesh, as you can see here. So you can close this, go to model browser and off this. This is a 2D meshing. This meshing is also hollow from inside. I will show you. If I mask a portion, so this meshing is also hollow. We need to do a 3D solid meshing. So now the next step, till this time I have done 2D meshing. So the first step is to perform 2D meshing. Then the next step is to check the connectivity, whether these 2D elements are completely connected or not. as we already checked the connectivity of my geometry, so 99.9% the elements will also be connected, but instead of assuming that these are connected, we will first check it whether they are connected or not. So press Shift F3 from your keyboard to enter to the connectivity panel, and from the drop box select elements. Shift left mouse button, drag the window, enter the tolerance value as 0.1, click on preview equivalence and click on find edges. Once you click on find edges, at the bottom you can see it should show a message that no edges were found, selected elements may enclose a volume. If you are getting an edges, that means the geometry is not connected, so the elements are not. So first you have to connect the geometry and then perform the 2D meshing. So once you are done with 2D meshing, now I will convert this 2D meshing to a 3D elements. But for that I need one more component. So my 2D elements will be in a different component and my 3D elements will be in a different component. So I will create a one more component from the component collector icons. Enter the component name as 3D hub. Without a property, I will assign the property later on and click on create. So I have just created a component so that I can move a 3D elements to the new component. Now go to 3D page to do 3D meshing. Go to 3D page. On 3D page, select tetra mesh. On 3D page, select tetra mesh. On this, select tetra mesh, the first option. In the first option, you can see there are two ways to convert a 2D mesh model into 3D. First is fixed tria chords to tetra mesh and the other one is float tria chords to tetra mesh. I personally recommend you to use fixed tria chords to tetra mesh, so that whatever chord 2D mesh, the way 2D mesh you are done, in the same way it will convert the 3D meshing. So from the drop box I will select, instead of components, element, select the components, select the option as mesh to current component. So whatever the component is bold, the new tetra, that is 3D meshing, will move to the new component which is in bolds, and click on mesh. So once you click on mesh, it will start creating the elements and my meshing is done. So you can see my meshing is completed now, and this is a 3D meshing. It is solid from inside, you can see. I will open this 2D mesh model also. So 2D elements are hollow and 3D elements are solid from inside. I will again repeat the process from the beginning till here, so that if you have missed any point, you can note it down again. So what I will do, I will delete this mesh, press F2, all delete. I will delete this component also. So this is my geometry. I have done the geometry editing. Now I will go to 2D page, auto mesh panel, select the surfaces, Shift plus left mouse button, enter the element size and click on mesh. This will generate the meshing. Click return. Again click return. Press Shift F3 from the keyboard. Select the elements. Enter the tolerance value as 0.1. Click on preview equivalence and find edges. Check the message that no edge were found. Selected elements may enclose a volume. Click return. Go to component character icon. Create a new component giving a different name and a different color. Click on create. Go to 3D page, tetra mesh panel, which is on 4th column, 1st row. Select the first radio button, that is tetra mesh. In the fixed triaccord to tetra mesh, I will select all the elements. Make sure the option mesh to current component should be there and click on mesh. Once you click on mesh, at the left side you can see it is processing the meshing and it has created 5932 nodes and generated the mesh. So my 3D meshing is done. So I can go to mask a portion of elements and you can check the 2D and 3D layers. So my meshing is done. Now the next step is to create the material property and update the components. So I'll off this. So I'll create the material as steel. You can use whatever material you want. Define a color. Define the type as isotropic. Card image as matte one. And click on create edit. Enter the values of E, new, row. By default it has taken the values of steel, so I will select these only. Then I will click on property collector icon where my mouse pointer is currently. Enter the property name as hub property. Define a color. Select the property type as 3D. Card image as P solid. Material as steel and click on create. So I have defined the material and property. Now the next step is to update the component. So I will go to component collector icon. Select the radio button as update. Click on comms. Select 3D hub. Toggle no property to property. Select the property, that is hub property. Click on update. I can check whether these elements have assigned the proper material or property not. So you can see if I select by material, I am getting the material color. If I am selecting by property, I am getting the property color. If I am selecting it by components, it is getting the component color. So the material properties have been selected. Now, as I already told you that in this webinar, I am going to show you how you can solve your model using HyperWorks products or HyperWorks tools. These webinars are not to tell you the exact procedure of how to do that, how you can do it. So I will off this. and see the results of displacement for the first load case and the animation. So when only torque is applied, you can see the value is coming very less, but when you can apply the stress here, you can see this is the stress value when only the torque is applied. Then when force X is applied, force in X direction, you can see the value of stress and displacement. Force in Y direction, the value of displacement and stress. Now the combined loading, when torque and force X is applied, then value of displacement and this, when force X and Y, torque and force Y is applied, then the displacement value. When the torque, force X and Y both are applied, then the value of displacement will be this and the value of stress will be this. So in this way you can solve a 3D component with multiple load cases and get your results done. So in this way I have completed the first model. Now I will show you how you can solve a Knuckle model or how you can perform the analysis on a Knuckle model. So earlier I have shown you the process where you have applied when you have done the meshing of 2D meshing and then you have converted that 2D elements into 3D elements. Now in this I am going to show you how to create a 3D elements directly. So to create a 3D elements directly, you can go to 3D page. On 3D page, select tetra elements, select volume tetra, select the surfaces, element types to R trias and click on mesh. So once you click on mesh, it will directly generate a 3D meshing. So you can see it has created a 3D meshing directly. If I mask this model, you can see it has created a 3D mesh. So this is the other way. One way is from 2D to 3D, the other way is from directly from geometry to 3D. I will again repeat it. I have a model file. This is the model file. So if I want to create a 3D tetra mesh, I will go to 3D page. On 3D page, select tetra mesh. On tetra mesh, I will select the third option as volume tetra. In the enclosed volume, I will select surfaces. Select the surface. Type as R triads. 2D type. 3D type is tetras. Check this two box, use curvature and use proximity, so it will create a smooth meshing. Enter the minimum element size according to your model. Enter the feature angle that you want, so that lesser the feature angle will capture the curvatures more, and average element size to be 4, and click on mesh. Once you click on mesh, it will automatically generate a 3D tetra meshing. So if I off this, you can see it has generated a 3D mesh. You can see here. Now on this structure also, I will show you how to apply the loadings and get the results out. So on the knuckle components also, we need to create the constraints and apply the forces the same way, but here I am going to show you only one load case. You can create the different load cases as per your requirement through as per your requirements, in the same way in which I have shown you on the hub. So you can create the same way on the knuckle also. So first press F4 from your keyboard. Create the center circle center, nodes between. I am going to constrain this and apply a force here. So I am going to just create 3 circle centers. And I am going to apply a torque in Z direction here also. So shift F2, remove the outer nodes. Then create one more component. Same way, go to 1D page, rigids. Select this node. Select the one node, biface, create. Select this node, biface, create. This node, biface, create. Select the independent node, dependent node, select biface and create. So I have created the rigids. Now I will create the material as steel. Property as knuckle. 3D card image P solid, material steel. Create edit. Then components, Sharing Knuckle, property update to Knuckle and update. Check property material. Now creating the loads, force, create, torque, create, SPC, create, analysis, constraints, applying the constraints, make current, apply the force, let's say in y direction, apply the torque in z axis, create one more as combine with a card image, load to combine these two loads, 1 1, force, torque, and a load step. I am going to create only one, which is the combine. Save the model. And try to see the results. There is an error. Let's see how we can solve this error. Okay, so the distance is very less. I will increase it to a certain extent. Save. Again, it is filling in the different one. So you have to check why these elements are failing. Similarly, it is failing in this because of the same reason. The distance is very, very less. Save. So the elements which are failing, you have to check those elements and solve it completely. So in this way you can edit the geometry and solve them. So I have solved this model. So this is the displacement plot for the load case combined, and this is the analysis plot for the same. If I have increased the deformation, so you can see here it is also twisting. If I mask this portion and increase the deformation further, you can see this portion is also twisting. So in this way you can solve the model and get the results and then decide whether this component is fail or not. So in this way I have ended with this today's session.